Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring an ecosystem that sits at the very edge of land and sea, where special forests thrive in a seemingly impossible environment. Mangroves grow where nothing else can. They plant their roots in shifting sands and have only salt water to survive on. At first glance, they can seem tangled and strange. But within their branches lies a world that quietly supports coastlines, shelters wildlife, and shapes the rhythm of entire ecosystems. As we explore these amazing forests, you might begin to get a sense of how alive they truly are. Beneath the surface, life moves through hidden channels and winding routes. Above the water, branches host creatures that depend on this delicate balance. Everything here is connected in ways that are easy to miss, yet powerful once seen. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, simply settle in. Let your shoulders soften. Allow your breathing to slow. And let your mind settle into stillness as we explore these remarkable ecosystems together. Let's begin. Mangroves are forests that can live where the sea invades the land. Most trees would die quickly in that borderland. Their roots would drown. Their cells would dehydrate in the salt. Their trunks would topple in unstable mud. Yet these forests make a home exactly where land becomes uncertain. They grow along tropical coasts, river mouths, and tidal estuaries, where the shoreline is never fully still. Twice a day, the water can rise, cover the ground, and retreat again, and still the forest remains. Life alone is strange enough to feel almost impossible. What makes it even more astonishing is that this harsh place does not become empty. It becomes crowded with life. Fish slip between roots. Crabs work the mud below. Birds hunt from above. In a place that seems too salty, too wet, and too unstable for a forest, mangroves create one of the richest living edges on Earth. Some mangroves breathe through roots that stick straight out of the mud. The mud beneath them is often packed tight and starved of oxygen, which means an ordinary buried root could suffocate there. So instead of relying only on what lies below, certain species send up thin spikes that rise into the air like pencils, pegs, or clusters of dark fingers. Each one is part of the root system. Each one is a breathing tool. Tiny pores let oxygen move inward when the tide is out, and that air is then carried to tissues hidden in the mud. It is such an odd solution that it can make a forest look less like woodland and more like a field of small instruments waiting in silence. Walk through one at low tide and you are seeing a tree solve a deadly problem in plain sight. It cannot flee the swamp. It cannot drain the ground. So it turns the ground itself into something it can breathe above. Mangroves can turn salty seawater into fresh water inside their leaves. They do not perform magic, but the result can seem close to it. Salt water surrounds them, presses into their world, and soaks the mud around their roots. For most plants, that would mean thirst, because salt makes it harder to draw in usable water. Mangroves survive by filtering, excluding, or expelling that salt through different strategies. In some species, the roots block much of it before it enters the plant at all. In others, special tissues handle what gets through, and leaves may store or release excess salt. The outcome is remarkable. Water inside the plant becomes far less salty than the water outside it. That is how a tree can stand in brine and still keep living cells supplied. Sometimes rejected salt even appears on leaves as a dusty coating or tiny crystals. These forests can survive tides that drown most other trees twice daily. Imagine living in a place where the ground disappears every morning and evening. The water rises over the roots, changes the chemistry of the soil, moves debris through the trunks, and then slides away again. For many plants, that constant flooding would be fatal. Oxygen would vanish around the roots. The soil would turn hostile. Seedlings would be uprooted before they ever had a chance. Mangroves endure that rhythm for years, even centuries, because their entire bodies are built around instability. Their roots anchor into shifting ground. Their tissues manage salt and water with unusual precision. Their growth follows the pulse of the tide instead of resisting it. A shoreline that seems unreliable to us is, for them, part of the daily schedule. That is one reason mangrove forests feel so extraordinary. They are not simply surviving despite the tide. They are living in conversation with it, day after day, flood after flood. Mangroves raise baby sharks, crocodiles, fish, and birds in one place. Few habitats serve so many young animals at once. Beneath the branches, the water is often shallow, shaded, and full of hiding places. The roots break up open space into a maze, which makes it harder for large predators to charge straight through. That gives juveniles a chance. Tiny fish gather there first, then larger youngsters follow, including species that later move out to reefs, open bays, or deeper rivers. In some regions, young sharks use these waters as nurseries. In others, crocodiles or alligators patrol nearby channels, while birds nest overhead in relative safety. The result is a layered nursery, with different creatures using different heights, depths, and seasons. One forest can shelter hatchlings, pups, fry, chicks, and nestlings all at once. It is difficult not to be amazed by that concentration of new life. A mangrove stand is not just a place where animals pass through. It is where many begin. Their tangled roots can stop waves before they reach the shore. When water rushes toward land, speed matters. Fast water hits harder, tears away soil, and carries more force into homes, roads, and fields. Mangrove roots interrupt that momentum. They stand in dense, tangled formations that force waves to split, curl, and lose energy. Instead of a clean run at the coast, water meets a living barrier with thousands of obstacles. Every root adds friction. Every trunk slows the flow a little more. During storms, that slowing effect can make a serious difference. It can reduce erosion, lower flood energy, and blunt the violence of incoming surges. This is one of the most astonishing things about mangroves. A forest that looks messy and unruly from a distance is performing protection with quiet precision. It does not need concrete or steel to matter. It simply stands in the right place, shaped by tide and mud, and turns a dangerous wave into something weaker before it reaches the land. Mangroves build new land by trapping mud, shells, and drifting sand. A coastline can seem fixed when seen on a map, but at ground level, it is always moving. Sediment arrives from rivers, currents, storms, and tides. Without something to catch it, much of that material keeps traveling. Mangrove roots act like sieves and hooks in the water. They slow the flow enough for suspended particles to settle. Fine mud drops first. Bits of shell and organic debris collect. Sand can lodge among roots and stay put long enough for more material to gather around it. Over time, the surface rises. What was once open water or unstable sludge can become firmer ground. This process is slow on human timescales, yet powerful over years and decades. The forest is not only occupying the shoreline, it is helping shape it. In that sense, mangroves are builders as much as survivors. They take what the sea delivers and gradually assemble new edges of land from the leftovers of motion. Some mangrove seeds start growing while still hanging on the tree. Most people picture a seed falling first and sprouting later, after it reaches soil and receives the right mix of water and warmth. Certain mangroves reverse that familiar sequence. Their seeds germinate while still attached to the parent. A long, green structure develops before release, already alive, already prepared for the next stage. This gives the young plant a head start in a difficult world. When it finally drops, it is no helpless speck. It is more like a ready-made spear of life, built to travel and then establish quickly when conditions allow. In some species, it can float for a time, carried by currents to another shore. If fortune favors it, the pointed end lodges in soft mud, and the seedling begins its independent life, almost at once. It is a remarkable strategy for a place ruled by water. In a shifting tidal world, beginning early can mean the difference between drifting away and taking root. A mangrove forest can feel like a swamp, a nursery, and a fortress. That mixture is part of what makes these places so memorable. At first, the mud, the standing water, and the dense roots can give them the mood of a swamp, with hidden channels and ground that seems to move underfoot. Then you notice how many young creatures are using the space, and the whole scene changes. Small fish flash in the shallows. Crabs work the banks. Birds choose branches above the reach of many dangers. It begins to feel like a nursery, busy with vulnerable life being kept just protected enough to grow. And then there is the final layer. Those same roots and trunks form a barrier. They complicate movement, break up waves, and shield the coast behind them. That is where the feeling of a fortress enters. Few habitats combine softness and defense so completely. Mangroves are muddy and vulnerable in appearance, yet they create shelter, resistance, and survival on a grand scale. These strange coastal trees help protect millions of people from storms. Their protection is not abstract. It reaches villages, towns, deltas, and island coasts where storm surge can race inland with terrifying speed. When mangroves remain intact, they can reduce the energy of that water before it strikes roads, crops, and houses. Their roots hold shorelines together. Their trunks and branches add resistance. Their presence can mean less erosion, less flooding, and less destruction when severe weather arrives. For communities living close to the sea, that can translate into saved property, safer farmland, and in some cases, saved lives. What makes this so striking is the scale. Mangroves are not rare curiosities helping a few isolated places. Across the tropics, vast numbers of people live near coasts that benefit from these forests. A tangled stand of salt-tolerant trees may not look dramatic from afar, yet in the path of a storm, it can become one of the most valuable living defenses on Earth. Mangroves grow on tropical coasts across more than 100 countries. They are not the specialty of one island, one sea, or one famous wilderness. These forests appear along shorelines in Africa, Asia, Australia, the Americas, and countless islands scattered between them. That wide reach is part of their wonder. A traveler can meet them in the Caribbean, in West African estuaries, in the deltas of South and Southeast Asia, and along remote Pacific coasts where the tides still govern the day. Yet each place gives them a different character. Some grow beside busy fishing towns. Others spread through immense river mouths or fringe coral lagoons. The species can change. The animals can change. The smell of the mud and the shape of the channels can change. Still, the same basic miracle keeps appearing. On coastline after coastline, trees have learned to occupy the shifting margin where salt water challenges nearly everything, and life gathers around them because of it. They thrive in places where rivers, tides, and forests all collide. Most landscapes are easier to describe than that. A river is a river. A forest is a forest. The sea is the sea. In mangrove country, those boundaries blur into one living zone of exchange. Fresh water arrives carrying silt, fallen leaves, and nutrients from far inland. Seawater pushes back with salt, current, and the force of the tide. The trees stand between the two, receiving both and belonging entirely to neither. That makes these coasts unusually dynamic. The water can change depth, direction, and chemistry in a single day. Sediment settles, then shifts. Channels widen, narrow, and migrate. Animals from inland waters, open coasts, and the canopy all use the same space in different ways. It is a meeting point in the deepest sense. Matter arrives from one world and is transformed in another. That constant collision is exactly what gives mangrove ecosystems their energy, complexity, and strange sense of being alive at every level. Mangroves live in mud so soft it can swallow an ordinary boot. Step into the wrong patch, and the ground may seem to vanish beneath you. What looks like solid earth can behave more like a slow liquid, made from fine sediment, decaying leaves, trapped water, and the remains of countless small organisms. This is not the kind of ground most trees would choose, because it shifts, compresses, and offers little firm support. Yet mangroves make a life there. They spread roots through material that can wobble, sink, and slump with the tide. That alone is impressive, but the softness of the mud also changes how the whole forest feels. Walking through it becomes cautious and uncertain. Each step reminds you that the shoreline is still being built. The forest is not perched on stable land that has existed forever. It occupies a place still in formation. There is something deeply fascinating about that. These trees are not merely growing on the coast. They are growing on instability itself. Their roots create underwater mazes where young animals can hide safely. In open water, survival can come down to whether a predator sees you before you find cover. Among these roots, sightlines break apart. Straight chases become awkward. Shadows overlap. Narrow gaps open into little chambers that are too confusing or too cramped for larger hunters to enter easily. For a small creature, that complexity can be the difference between life and death. What looks chaotic from above becomes precise shelter below. Tiny bodies can slip between root loops, pause in still pockets of water, and feed in relative safety while danger passes nearby. The structure does more than block an attack. It creates a three-dimensional world of ledges, screens, and escape routes. That is why mangrove edges can hold so much hidden motion. A single root mass may contain dozens of creatures using different depths and angles at once. It is a brilliant natural design, built by trees yet shaped perfectly for underwater secrecy and survival. Many mangroves survive by filtering salt at the root before it enters. This is one of the most elegant solutions in the natural world. Salt surrounds the plant, but too much salt inside living tissue is destructive. So instead of allowing seawater to pass freely inward, certain species create a barrier at the root surface that blocks much of the salt while still letting water move through. It is not perfect. Some salt still gets in. But the reduction is enough to make life possible in a place that would otherwise be chemically overwhelming. The brilliance of this strategy lies in where it happens. The battle is fought early, before the problem spreads through the trunk, branches, and leaves. In effect, the tree is screening what enters its body at the threshold. That turns the root into something more than an anchor or a drinking organ. It becomes a selective gatekeeper. Once you understand that, a mangrove coastline starts to look less like a swamp and more like a vast collection of living filtration systems. Other species push salt out through special glands in their leaves. Not every mangrove solves the problem at the root. Some allow more salt to travel upward, and then deal with it later, using tiny glands in the leaves to expel the excess. That means the leaf is not just gathering sunlight. It is also handling waste from a chemical struggle the tree faces every day. On the surface, this seems risky, almost wasteful, yet it works. Salt moves outward, collects on the leaf, and can be washed away by rain or blown off by wind. The image is astonishing when you stop and think about it. A tree standing in a tidal swamp is actively shedding the sea through its own foliage. This strategy also reveals that mangroves are not one single invention repeated everywhere. They are a collection of different solutions to the same difficult problem. Even within one habitat, evolution has produced multiple answers, each one strange, practical, and surprisingly beautiful in its own way. Some mangrove leaves sparkle with tiny crystals of rejected salt. At the right moment, a branch can look as though it has been dusted by frost. What catches the light is not ice and not sand, but salt that the plant has forced back out to the surface. It is one of those details that transforms a scientific idea into something immediate. You do not need a diagram to understand it. The tree is showing you the evidence on its own skin. In a harsh coastal world, that glitter is proof of a hidden process of control, balance, and survival. It also changes the way you see a leaf. What seems like a simple green surface is doing far more than making food from sunlight. It is part of the tree's defense against dehydration and chemical stress. Even the shine has a story behind it. In mangroves, beauty often turns out to be practical. A small sparkle on a leaf can reveal an entire strategy for living with the sea. Their roots can pull oxygen from air when the mud has none. Buried in waterlogged sediment, roots face a serious problem. Oxygen disappears quickly in that kind of ground because microbes use it up and fresh supplies do not move in easily. For many plants, that would shut down normal root function. Mangroves avoid that trap by connecting hidden tissues below the surface to structures exposed to the air. Oxygen enters through pores when conditions allow, then travels through spongy internal passages to parts of the root system that would otherwise be trapped in suffocating mud. The elegance of this arrangement is easy to miss because so much of it happens out of sight. Nothing dramatic announces it. No movement. No sound. Yet the tree is effectively plumbing air downward into a place that cannot provide it. Once you know that, the whole forest feels more inventive. These are not trees passively enduring a difficult habitat. They are reorganizing the flow of a life-giving gas so they can inhabit ground that should defeat them. Pencil roots rise from the ground like a forest of breathing straws. At low tide, the mud can bristle with so many of them that the ground appears covered in spikes. Each one is narrow, upright, and strangely deliberate, as if the buried root system has decided to send up a field of periscopes. The effect is visually unforgettable. It does not look like a normal woodland floor at all. It looks engineered, almost mechanical, though it is entirely alive. Those upright structures help the tree exchange gases with the atmosphere when the sediment below is starved of air. In practical terms, they are lifelines. In visual terms, they give the forest a character unlike any other. They also change the experience of moving through the habitat. You cannot stride carelessly across such a surface. You have to slow down, watch your footing, and notice the pattern. That forced attention is part of the fascination. A mangrove forest asks you to look closely and then rewards you with forms that seem almost impossible. Stilt roots hold certain mangroves upright like living wooden scaffolding. Some species rise above the mud on angled supports that arch from the trunk and branches into the ground below. They look less like ordinary roots and more like the braces of a structure built by a patient carpenter. This arrangement gives the trees stability in places where the substrate can shift, soften, and erode. Instead of trusting one buried anchor, the plant spreads its weight through many points of contact. That makes it harder for waves, currents, or unstable sediment to topple the whole tree. There is also something theatrical about the form. A shoreline lined with these rooted arches can seem like a city of stilts built by nature itself. Fish move beneath them when the tide is high. Shadows lace the water. The trunk appears suspended above the world it depends on. It is a vivid reminder that mangroves are structural innovators. They do not merely grow in a difficult place. They redesign themselves to stand there. Buttress-like root systems help some species grip shifting coastal ground. Along some mangrove shores, the earth never truly settles. Sediment arrives, slips away, compacts, and loosens again with the movement of tides and currents. In that restless setting, broad flaring roots can spread from the base like supports built for a moving floor. They brace the trunk against tilting and help distribute force through a wider patch of unstable ground. The effect is impressive even before you understand it. A tree can seem to be standing on its own foundation, as though it anticipated the coast would not stay still. That matters because a shoreline is not just soft, it is dynamic. Water cups channels, deposits fresh layers, and reshapes the surface from season to season. These root forms are part anchor and part architecture. They reveal that survival here is not about brute strength alone. It is about balance, leverage, and the ability to remain upright while the world beneath you keeps changing. Mangrove bark can store tannins so strong, they once preserved fishing nets. Long before chemistry came in labeled bottles, coastal people learned to read the useful powers of local plants. Mangrove bark was one of those discoveries. In certain species, it contains high levels of tannins, bitter compounds that can stain, preserve, and protect materials from decay. Fishers in some regions soak their nets in bark extracts to help the fibers last longer in harsh, wet conditions. That detail opens a wonderful window into the relationship between people and these forests. Mangroves were not only admired from a distance, they were studied through experience and woven into working life. A tree growing in salt and mud became part of the daily technology of survival at sea. There is something satisfying about that chain of knowledge. A forest evolved its own chemical defenses, and human communities learned how to borrow them. What seems like rough bark on the outside can hold a history of craft, observation, and practical ingenuity. Their leaves are thick and waxy to conserve precious fresh water. On a salty coast, water can be everywhere and still remain difficult to use. That is why many mangrove leaves feel more substantial than the leaves of inland trees. They're often thick, tough, and coated in a waxy surface that helps reduce water loss under sun and wind. This is not luxury. It is survival in a place where dehydration is a constant threat. Salt in the surroundings makes fresh water harder to obtain, so every drop inside the plant becomes more valuable. The leaf must hold onto it carefully. Seen from afar, that glossy surface may look simple enough. Up close, it tells a deeper story. The tree is managing a budget of moisture in an unforgiving environment, and the leaf is one of its most disciplined tools. Instead of behaving like a delicate green ornament, it becomes a compact reservoir, shield, and shielded solar panel all at once. Some mangroves can pause growth during extreme salt stress and heat. Not every challenge can be met by pushing forward. Sometimes survival depends on restraint. In especially harsh conditions, certain mangroves reduce growth and enter a kind of protective slowdown. When salt levels climb and heat becomes intense, building new tissue can be too costly. Water is harder to manage. cells come under stress. So the tree shifts priorities. Rather than spending energy on expansion, it focuses on endurance until conditions improve. That is a remarkable strategy because it shows a different kind of strength. These trees are not always racing to grow taller or spread faster. They know when to wait. In a coastal world ruled by season, drought, and fluctuating salinity, patience can be as important as vigor. There is a quiet drama in that. A mangrove may appear still and unchanged, yet inside it is making decisions about risk, survival, and timing. Sometimes the most successful response to hardship is simply not to waste yourself. Mangroves do not all look alike, even within one estuary. At first glance, a newcomer might see only a wall of coastal trees and assume it is one kind of forest repeated again and again. Spend a little more time there, and that impression falls apart. Some species stand on dramatic arching supports. Others send up upright spikes from the mud. Leaves vary in shape, color, and texture. Trunks differ in form. Even the spacing of trees can change from one part of an estuary to another. This diversity matters because it reveals that a mangrove habitat is not a single design. It is a community of related solutions, each adjusted to slightly different conditions of flooding, soil, and salinity. That is part of what makes these forests so absorbing to explore. A bend in the channel can alter the scene. A rise in the ground can introduce a new dominant species. The forest keeps changing its face while still remaining unmistakably itself. Red mangroves often stand closest to open water on arching roots. They are among the most iconic members of the coastal forest, and it is easy to see why. Their roots descend in looping arches that seem to lift the trees above the tide, while also tying them to it. Because they commonly occupy the seaward edge, they are often the first line you notice from a boat or shoreline. They stand where waves and currents are most immediate, meeting the open water with a form that looks both elegant and practical. Those arching supports help stabilize the tree in saturated ground and create shaded spaces beneath where aquatic life can gather. Visually, they are unforgettable. A fringe of them can look like a colonnade built by the sea itself. Ecologically, they are equally striking. By occupying that watery frontier, they help define the border between coast and channel. They do not just grow beside the water. In many places, they seem to step directly into it. Black mangroves usually colonize higher ground with fields of upright root spikes. Move slightly inland from the watery edge, and the scene can change dramatically. Here, in places flooded less deeply or less often, black mangroves often take over. Their presence is announced by crowds of narrow projections rising from the mud around them. These root spikes can make the ground look almost porcupine-like, dense with life reaching upward from below. The trees themselves may seem less theatrical than their red relatives at first, but the landscape they create is just as distinctive. Higher ground in a mangrove system does not mean dry ground in the ordinary sense. It still lies under the influence of salt, tide, and waterlogged soils. It is simply a different zone of difficulty, and black mangroves are especially well suited to it. That shift from arching coastal roots to bristling interior spikes shows how subtly these forests sort themselves. A small change in elevation can produce a whole new architecture. White mangroves often grow farther inland where flooding is less severe. By the time you reach their favored ground, the daily struggle with open water has eased a little. The soil may still be salty and the tides still important, yet the setting is often less exposed than the outer fringe. White mangroves are commonly associated with those quieter interior zones, where inundation tends to be shallower or less frequent. That placement gives them a distinct role in the layered geography of the forest. They are part of the same mangrove world, but they occupy a different chapter of it. Their position also helps reveal something important about these ecosystems. Conditions do not change only from country to country. They can shift over a few steps of shoreline. A subtle rise in land can mean different flooding, different salinity, and different dominant trees. White mangroves remind us that even a muddy coast has gradients, and those gradients are enough to shape which kind of forest appears before you. Buttonwood is often called a mangrove neighbor rather than a true mangrove. It grows close enough to the tidal forest that many people associate it with mangroves immediately, yet botanists often place it just outside the inner circle. Buttonwood usually occupies higher, less frequently flooded ground along the landward edge, where salt still matters, but the conditions are no longer quite the same as those faced by the core mangrove species. That makes it a fascinating border character. It belongs to the story without fitting neatly into the main cast. In practical terms, it helps mark the transition from tidal woodland to more terrestrial vegetation. In imaginative terms, it feels like a companion that travels with the mangroves but keeps one foot on firmer ground. I love that detail because it reminds us that nature does not always honor the boundaries people prefer. Some species sit right on the edge of definition, close enough to resemble one world while already leaning into another. Mangrove forests can shift in zones depending on salt, mud, and tide. What looks like a single green mass from far away can actually be arranged in bands, each shaped by a different combination of flooding, soil texture, and salinity. Near open water, one species may dominate. Farther inland, another takes over where the ground sits slightly higher, or the mud holds different chemistry. This zoning can be subtle, but once you notice it, the forest begins to read like a map. The position of each tree tells you something about the conditions beneath it and around it. That is one of the most satisfying things about mangroves. They are not random. They organize themselves according to gradients that the eye can learn to follow. A shoreline becomes a pattern of ecological preferences written in roots and leaves. This also means the forest is sensitive to change. Alter the water flow, sediment supply, or salt balance, and those living zones may shift with surprising speed, redrawing the coastal map. One coastline can host several mangrove species in a delicate natural order. Stand in one place long enough, and the shoreline begins to reveal a pattern. Trees nearest the water are not always the same as those standing a little farther back, and those are not always the same as the ones closer to dry land. This arrangement is not accidental. Each species is responding to its own preferred balance of flooding, salinity, and soil conditions. The coast becomes a living sequence, with one group giving way to another as the ground rises or the water changes. What makes this so fascinating is how fine the differences can be. A small shift in height, one you might barely notice with your eye, can be enough to favor another kind of tree. The result is a subtle order written across the edge of the sea. It feels almost musical, as though the forest is arranged in notes, each species entering when the conditions are exactly right for its part. Their floating seedlings are shaped like green darts ready for travel. They do not look like the seeds most people carry in their minds. There is no dry shell, no tiny bean, no papery wing. Instead, many mangroves produce long, tapered seedlings that already seem built for the journey ahead. Smooth, green, and pointed, they can look like little spears suspended from the branches. That shape is not merely striking. It is useful. It helps the young plant drop, float, and later lodge in soft ground when the moment comes. Even before release, there is a sense of direction about them. They appear less like beginnings and more like prepared departures. That is part of their charm. A mangrove seedling does not seem passive. It seems poised. Hanging there above the tide, it looks as though it is waiting for a current, a shoreline, and a chance. Few plants make their next chapter look so visible before it has even begun. A mangrove seedling can drift at sea before rooting elsewhere. Once released, the young plant does not always settle immediately beneath its parent. It may be carried away by currents, pushed along estuaries, or swept into coastal waters where it drifts for days or even longer before finding a new home. That ability changes the scale of the story. A mangrove forest is not only local, it can send living descendants outward on the sea itself. There is something thrilling about that image. A small green traveler moves over shifting water, exposed to weather, wave action, and chance, yet still remains viable. The seedling is not simply surviving the voyage. The voyage is part of its design. It gives the species reach. It allows new shorelines to be tested. It turns the coastline into a connected world of possible landfalls. What begins in one muddy forest may end on another distant shore, carried there by tide and current, like a message that already knows how to grow. Some propagules stay dormant while floating, waiting for the right shore. Drifting is only half the achievement. The other half is restraint. While floating, certain mangrove propagules can hold themselves in a suspended state, alive but not rushing into growth at the wrong moment. That patience matters because open water is no place to put down roots. A seedling that commits too early would waste its chance. So instead it waits, carried along until it meets conditions that promise real survival. I find that deeply compelling. The plant is not only mobile, it is selective. It can endure uncertainty without spending itself too soon. In a world of tides and chance landings, that kind of timing is a quiet superpower. It turns wandering into strategy. The sea becomes less of a threat and more of a road, one that can be traveled without panic. A floating propagule may look simple, yet inside it is holding back an entire future until the coast is finally right. When conditions align, a drifting seedling can stab into mud tip first. After all that waiting, the landing can be beautifully decisive. The narrow end points downward, the current eases, the water depth is right, and the soft substrate receives the seedling like a target. Instead of washing away again, it catches. That moment is one of the great little dramas of the mangrove world. A traveler that has floated between chance and risk suddenly becomes anchored. The shape that helped it journey now helps it settle. Once lodged, it has an opportunity to establish before the next strong movement of water tears it loose. You can almost feel the tension in that first grip. Will it hold through the tide cycle? Will it survive long enough to root firmly? So much depends on this one elegant contact between plant and mud. What seems like a simple drop is actually a precise act of timing, buoyancy, and form, all coming together in a single successful strike. Mangroves can colonize new coastlines, one floating seedling at a time. Forests can feel permanent when fully grown, but every great stand begins with arrivals. Along a bare or disturbed shore, one seedling may lodge, survive, and become the starting point for something much larger. Then, another arrives, and another after that. Over time, scattered individuals can become a fringe, and the fringe can become a forest. This slow expansion is one of the reasons mangroves are so captivating. They are not planted by hands or carried by birds in the usual way. They use the coastline itself as a route for advance. Currents deliver possibility in slender green forms, and the shore accepts or rejects them according to its own conditions. It is colonization by persistence rather than speed. No single arrival seems dramatic on its own, yet together they can transform a landscape. An open, muddy edge can gradually become rooted, sheltered, and alive because the sea keeps bringing the next beginning. Tides act like conveyor belts for mangrove reproduction and expansion. Every rise and fall of water moves more than the eye can easily follow. Leaves, sediment, larvae, and young plants all travel with it. And among the most important passengers are mangrove propagules. The tide lifts them, carries them through channels, turns them around bends, and leaves them in new positions as the water retreats. In that sense, the forest is using the daily pulse of the sea as a transport system. Nothing mechanical is visible, yet the effect is wonderfully similar to a moving belt, always operating, always sorting, always redistributing. This makes reproduction feel less like a single event and more like an ongoing coastal process. Each tide is another chance for dispersal. Each cycle can place young plants where they were not before. What seems repetitive from a human perspective becomes incredibly productive from the perspective of the forest. The same water that challenges mangroves also helps carry their future from one stretch of shore to the next. Mangrove flowers are often small, but they feed bees, bats, and moths. The roots and seedlings tend to steal the attention, which makes the flowers feel like a hidden chapter. Many are modest in size and easy to overlook from a distance, yet they provide food for a surprising range of visitors. Bees may arrive by day, moving among blossoms in search of nectar or pollen. In some places, bats and moths also play a role, linking these tidal forests to the wider world of pollination that people often associate with gardens or inland woods. That contrast is part of the delight. In a habitat famous for mud, salt, and twisted roots, there is also this softer exchange between flower and flyer. It reminds us that mangroves are not only defensive and rugged, they also participate in one of the most delicate processes in nature. The future of the forest can depend on tiny visits, brief feedings, and the quiet movement of pollen between blossoms no bigger than a passing glance. Some mangrove blossoms open at night for very different pollinators. Daylight does not tell the whole story of a mangrove forest. After sunset, another shift begins. Certain blossoms open or become especially active at night, and that change invites a different cast of visitors. Instead of daytime insects alone, the forest may receive night-flying moths or nectar-feeding bats that move through the darkness with remarkable precision. This is such a marvelous detail because it reveals a hidden timetable inside the trees. The flowers are not simply there. They are scheduled. They open in ways that match the habits of the creatures most likely to serve them. A shoreline that seems quiet after dark may actually be engaged in crucial exchanges above the mud and water. Pollination continues, but under another set of senses, another rhythm, and another sky. Once you know that, a mangrove night feels transformed. What appears still and shadowed may be full of purposeful visits, but keep the forest reproducing until morning returns. Nectar from mangrove flowers can produce distinctive local honey. This is one of those beautiful moments where ecology meets human taste. When bees forage among mangrove blossoms, the nectar they gather can produce honey with a character tied to that specific coastal landscape. The flavor, color, and aroma may vary by species and region, which means the honey becomes a kind of edible map of place. It carries the signature of a tidal forest into something you can hold in a jar. I love that because it makes the connection between people and mangroves feel intimate and immediate. The forest is not only protecting shorelines or supporting wildlife in ways that scientists measure. It is also offering a sweetness shaped by salt-edged air, local blossoms, and the movement of bees through a very unusual habitat. Even here, in something as familiar as honey, mangroves remain distinctive. Their strangeness does not stay trapped in the mud. It can travel outward as flavor, memory, and local identity. Crabs are among the busiest gardeners in a mangrove forest. Look down for a moment and the whole ground seems to come alive with work. Crabs scuffle between roots, vanish into burrows, emerge with scraps, and begin again. They are not just passing through. They are constantly shaping the place. By feeding on fallen leaves and other organic debris, they break larger material into smaller pieces that microbes can process more easily. That helps move nutrients through the system instead of letting everything simply pile up on the surface. Their digging changes the texture of the mud and the movement of water through it. Their daily traffic redistributes food and sediment in ways that seem tiny at first, yet become enormous when repeated by thousands of animals across a forest floor. What fascinates me is how easy they are to underestimate. They look like background life, yet they are maintenance workers of the entire ecosystem, keeping the muddy engine of the forest in motion. Some crabs drag mangrove leaves underground and reshape the forest soil. A fallen leaf does not always stay where it lands. In many mangrove forests, crabs seize it, tug it across the mud, and pull it down into a burrow like treasure being smuggled below ground. There it may be eaten in parts, stored or left to break down in darker, wetter conditions than the surface provides. This simple act has surprising consequences. Organic matter gets moved downward into the sediment, which changes how nutrients are distributed and how the soil develops over time. The crab is not thinking like an engineer, yet the effect is engineering all the same. Leaf by leaf, burrow by burrow, the ground is altered from within. I love this because it turns a humble scene into something grand. What looks like a small animal stealing lunch is also a force that helps build the hidden character of the forest floor. Beneath the roots, the soil is being edited by claws. Fiddler crabs help aerate mud by digging thousands of tiny burrows. Seen from above, the mud can resemble a pocked landscape, full of little openings that lead into narrow tunnels below. Many of those entrances belong to fiddler crabs, restless diggers that spend their lives moving sediment and maintaining burrows. Each hole may seem trivial on its own, but together they transform the upper layers of the ground. Air can penetrate more easily. Water drains and refills in new patterns. The mud becomes less sealed off from the world above. That matters in a habitat where oxygen is often scarce, and the sediment can become chemically harsh. The crabs are, in effect, ventilating the forest floor. There is something wonderfully disproportionate about that. A creature small enough to fit in your hand can influence conditions for microbes, roots, and other animals simply by going about its ordinary routine. The whole landscape benefits from a labor no one assigned and almost no one notices at first glance. Mud skippers hop across mangroves like fish that briefly borrowed legs. The first time you see one, it can feel like a prank played by evolution. Here is a fish out of water, propping itself up on sturdy fins, wriggling, hopping, and pausing on exposed mud, as if the usual rules had been suspended. Mud skippers belong perfectly to the in-between world of mangroves because they are specialists in edges. They can breathe in ways that allow them to spend surprising amounts of time out of the water, provided they stay moist, and they use the intertidal flats as feeding and social spaces when the tide recedes. Their eyes sit high, giving them a watchful, almost cartoonishly alert expression. Yet nothing about them is comic once you realize how finely adapted they are. They occupy a border between fish life and something almost terrestrial in appearance. In a forest already famous for bending expectations, they add one more astonishment, a reminder that mangrove mud invites unusual experiments in how an animal can live. Archerfish hunt among mangrove roots by shooting insects from branches. This is one of the most precise hunting tricks in the natural world. An archerfish waits below overhanging vegetation, watching for an insect perched above the water. Then it fires a jet from its mouth with enough accuracy to knock the target loose. The insect falls, and the fish snaps it up. In mangrove channels where branches lean over tidal water and insects gather near the foliage, that strategy becomes especially effective. The fish is not merely swimming through the forest. It is using the forest as a shooting gallery. What makes the scene so marvelous is the combination of patience, aim, and calculation. The fish must judge position and compensate for the strange optics of looking through the water's surface at prey in air. It succeeds anyway. That turns an ordinary branch into part of an ambush zone. In a place full of tangled roots and shifting tides, even the hunters can behave like tiny physicists. Juvenile reef fish often spend their earliest months hidden in mangroves. When people picture reef fish, they usually imagine bright adults weaving through coral in clear blue water. What is easy to miss is that many of those same species begin life in a very different setting. The earliest months may unfold in the shelter of mangrove channels, where the water is often calmer and the root systems provide protection during a vulnerable stage. There, small bodies can grow before facing the greater hazards of the open reef. That link between muddy forest and coral paradise is one of the most beautiful connections in coastal ecology. It means a fish that dazzles divers later in life may owe its survival to a tangle of dark roots near shore. The glamour of the reef begins in obscurity. I find that deeply satisfying. It reminds us that spectacular ecosystems are often supported by humbler ones nearby, and that the story of a reef does not begin at the reef itself. Young barracuda and snapper may begin life among mangrove roots. It is a wonderful reversal of expectation. Barracuda are famous for speed and menace. Snapper are associated with reefs, fisheries, and open coastal waters. Yet their earliest chapter can unfold in the comparative shelter of a mangrove nursery. As juveniles, they need protection more than drama. The root-filled shallows offer cover, food, and fewer opportunities for larger predators to corner them. So the future hunter begins as something hidden, cautious, and small among the maize. That is part of what makes mangroves so compelling. They hold the first drafts of creatures we usually picture in their adult forms. A sleek predator of later life may once have been just another youngster threading through a muddy forest edge. Seen this way, mangroves are not only habitats, they are beginnings. They hold the vulnerable stage before confidence, before speed, before the open sea. Great fish are often made in places that seem modest at first glance. Some sharks use mangrove shallows as safe nurseries for their pups. The word shark tends to summon open water and powerful movement, not quiet shallows beneath coastal trees. Yet for certain species, mangrove areas provide exactly what the young need most. The water can be shallow enough to discourage some larger predators, and the structural complexity offers additional refuge while the pups grow stronger. Food may also be plentiful, allowing them to feed without roaming far. This makes the nursery role of mangroves feel almost startling. A habitat many people think of as muddy and still is also part of the early life of one of the sea's most iconic predators. That contrast is irresistible. It reminds us that even formidable animals begin with vulnerability. Before a shark becomes a symbol of confidence in open water, it may spend time in a world of roots, shadows, and cautious movement near shore. The forest is not just sheltering small fish, it is sheltering the future shape of marine power. Crocodiles and alligators often patrol mangrove channels with surprising stealth. A mangrove creek can seem empty until it suddenly does not. The water is dark, the banks are tangled, and the channels curve out of sight. In that setting, crocodiles and alligators are masters of understatement. They can move with such little disturbance that the first sign of them may be a set of eyes, a slight ripple, or a shape that turns out not to be driftwood after all. Their presence adds a primeval edge to these forests. Mangroves already feel ancient in their own way, but the arrival of a large reptile sliding through the channels deepens that impression at once. This is not a decorative wilderness. It is a place where major predators still move almost invisibly through the tidal maze. That matters for the ecosystem, but it also matters for the atmosphere. The forest becomes charged with possibility. Even still, water feels alert when you know something powerful may be gliding beneath it. Mangroves shelter nesting herons, egrets, kingfishers, and spoonbills overhead. Lift your eyes above the mud and roots, and an entirely different world appears. Branches become lookout posts, nesting sites, and hunting perches for birds that depend on the richness below. Herons and egrets may stand poised with patient intensity. Kingfishers add flashes of color and speed. Spoonbills bring a silhouette so distinctive they can seem almost unreal when seen against the sky. What makes this so lovely is the vertical layering of the habitat. Crabs work below. Fish move through the channels. Reptiles patrol the water. And above it all, birds build families, rest, and search for food. The forest is functioning in stacked dimensions, with the canopy and upper branches offering a second realm of life above the tidal one. For a listener, I think that is part of the enchantment of mangroves. They are not only dense and muddy, they are also airy and alive with wings, watching the water from above. Monkeys in some regions feed, travel, and sleep in mangrove forests. For many people, monkeys belong to mountain jungles or inland rainforests, not tidal woods that fill and empty with the sea. Yet in some coastal regions, troops move confidently through mangroves as though the roots and channels were made for them. They feed on fruit, leaves, flowers, and small animals. They use branches as raised pathways above mud that would slow almost anything on the ground. And when night comes, some settle into the trees to rest above the shifting water. That image alone is extraordinary. A mangrove forest is already a meeting place of land and sea. Add monkeys to it, and the place seems to stretch the imagination even further. These are not animals merely visiting by accident. They are using the habitat as part of daily life, reading the tides, the branches, and the food sources with confidence. It reminds us that mangroves are not marginal scraps of nature. They are full, functioning worlds. Tigers have hunted through mangroves in the tidal forests of the Sundarbans. There is something almost unbelievable about the idea at first. A tiger feels like a creature of dry ground, tall grass and forest shade, not one of mudflats, salt air, and tidal creeks. Yet in the Sundarbans, that great cat has moved through a landscape shaped by water as much as land. The setting changes everything about how you picture the hunt. Instead of firm earth and clear trails, there are muddy banks, narrow channels, shifting islands, and a forest that can be flooded and exposed in turn. That means every movement is negotiated with the tide. Every path may vanish or soften. It gives the tiger a setting as dramatic as the animal itself. I think this fascinates people because it feels like the natural world refusing to stay simple. Even one of the most iconic predators on Earth can belong to a place stranger than many would ever imagine, where wilderness and water are woven together. The Sundarbans is the largest mangrove forest on Earth. Scale matters, and a scale here is difficult to hold in the mind. This is not a small fringe of coastal trees or an isolated pocket of swamp. It is a vast tidal forest spread across a mighty delta, with channels, mudflats, and wooded islands extending over an immense area. Knowing that the largest mangrove forest on the planet exists at such grandeur changes the way you think about these ecosystems. Mangroves stop being a curiosity at the edge of the map. They become one of Earth's major living landscapes. The name itself, Sundarbans, has a weight to it because it represents something almost archetypal, a tidal wilderness where river and sea meet on a colossal scale. That size also means complexity. Countless channels, countless organisms, countless interactions unfold there at once. It is not only large in area, it is large in ecological importance, in cultural presence, and in the sheer depth of imagination it invites. Bengal tigers there live in a world of mud, tide, and salt. That combination reshapes the animal in your mind. We are used to imagining tigers in forests with dry leaf litter and firm paths under paw. In the Sundarbans, the great cat inhabits a far more unstable world. The ground may be soft and slick. Water enters and leaves with the tides. Salt influences the vegetation, the prey, and the very feel of the landscape. To live there is to adapt not only to other animals, but to the pulse of the coast itself. The result is a tiger story, unlike any other. This is not merely a famous predator placed in a new setting for dramatic effect. It is a population existing inside a genuinely demanding environment that asks different things of movement, territory, and survival. That is what makes it so memorable. The tiger remains powerful and recognizable, yet the world around it becomes strange enough to make the familiar animal feel newly mysterious again. Saltwater crocodiles rule some mangrove estuaries as ancient apex predators. Few animals fit the atmosphere of a mangrove estuary more perfectly. Saltwater crocodiles seem almost designed for dark channels, muddy banks, and places where stillness can turn dangerous without warning. They can wait with extraordinary patience, showing little more than eyes and nostrils above the surface, while the rest of the body disappears into water the color of tea or silt. That quiet power gives mangrove waterways an ancient feeling. These reptiles carry the presence of a much older world into the present, and in some estuaries they sit at the top of the food web with very little to challenge them. I think that is why people find them so haunting. They do not need speed or spectacle to dominate the imagination. Their authority comes from calm, mass, and timing. In a habitat already shaped by hidden roots and concealed movement, a great crocodile feels like the final proof that the forest is deeper and wilder than it first appears. Fireflies can turn certain mangrove trees into living constellations at dusk. As daylight thins, the forest changes character. Edges soften, channels darken. Then, in some places and at certain times, points of light begin to appear among the branches. One flash becomes many. Soon a tree may seem sprinkled with stars, each pulse coming from an insect no larger than a small leaf. The effect is enchanting because it transforms the mangrove from something earthy and tidal into something almost celestial. Mud and roots remain below, but overhead the branches glitter as if the night has descended into the canopy in pieces. This is not just pretty. It is one of those rare moments when an ecosystem feels theatrical without ceasing to be real. Courtship, signaling, and insect life create a spectacle that seems designed for wonder. It reminds us that mangroves are not only habitats of survival and struggle. They can also stage moments of beauty so strange that they feel half-dreamed. Mangroves can host oysters, barnacles, and sponges directly on their roots. In many places, the roots do far more than support the trees themselves. They also become living real estate for animals that need a hard surface in the water. Oysters may cluster there. Barnacles may cement themselves in place. Sponges may attach and filter the surrounding water. Suddenly, a root is not only a plant structure, it is a vertical neighborhood. That is a marvelous twist, because mangrove habitats are usually associated with mud, and mud does not offer many firm places for attached marine life. The tree solves that shortage simply by being there. It lifts solid surfaces into a soft world, and other organisms take advantage of the opportunity. I love how this blurs the line between plant and habitat. The mangrove is not just surrounded by life. Life is physically layered onto it. Each submerged root can become a little reef-like column, busy with creatures that would otherwise have nowhere convenient to settle. Their submerged roots become hard surfaces in places where mud dominates everything. That might sound simple, but in a muddy estuary, it is a profound ecological gift. Soft sediment covers the bottom and shifts with water movement. Many organisms cannot anchor well in such conditions because they need something firm to cling to, crawl across, or colonize. Mangrove roots change that equation. They descend into the water as solid structures, making vertical surfaces available where very few existed before. Once that happens, the whole habitat becomes more complex. Animals that require attachment points gain a foothold. Others come to feed on them. Small fish find more texture, more shelter, and more opportunity. The forest effectively adds architecture to an otherwise yielding environment. That is one reason mangroves feel so rich. They create contrast. Hard and soft exist side by side. Water and wood overlap. A place that could have remained a flat, muddy margin becomes three-dimensional, layered, and unexpectedly intricate because the roots supply structure where structure was scarce. Even tree-climbing snails can spend their lives in mangrove canopies. It is a delightful reminder that mangroves are full of creatures people never expect. A snail sounds like a resident of garden stones, damp walls, or leaf litter, not of tidal trees standing above brackish water. Yet some species climb trunks and branches, living much of their lives above the mud in the mangrove canopy. That detail matters because it reveals how many niches this habitat creates. The forest is not only for swimmers, waders, and burrowers. It also supports slow-moving climbers that navigate bark and leaves in a world influenced by salt and tide. There is something charming and almost improbable about it. A listener may picture the mangrove as dramatic, tangled, and full of conspicuous wildlife, then suddenly discover that even snails have found a place in its upper reaches. The habitat becomes more intimate at once. Not every marvel is large. Some are tiny, deliberate, and hiding in plain sight on the trees. Some mangrove insects time their lives around tides and moonlight. In a place ruled by rising water, timing can become everything. For certain insects, it is not enough to respond to daylight or season alone. Their activity, emergence, or reproduction may also be shaped by the rhythm of tides and the changing brightness of the moon. That creates a wonderful sense of layered clocks operating within the forest. Water level provides one schedule. Lunar light offers another. The insects live by both. It means the mangrove is not merely a backdrop for life. It is a timing system, a place where celestial cycles and coastal motion are woven into the lives of very small creatures. I find that deeply beautiful because it turns even insect behavior into part of a larger pattern. The moon above and the tide below are joined through the bodies of tiny animals no one may notice at first glance. In mangroves, even the smallest lives can be tuned to the grand mechanics of earth and sea. Mangroves trap fallen leaves that feed entire food webs as they decay. When a leaf drops in an inland forest, it usually lands on dry ground and begins a familiar return to the soil. In the mangrove forest, that falling leaf enters a very different fate. It may settle in wet sediment, snag among roots, or drift briefly before being caught in the tidal maze. There, it becomes fuel. As the leaf softens and breaks apart, it feeds a chain of life that stretches far beyond the tree that made it. Tiny organisms begin the work. Small animals take advantage of what follows. Larger feeders benefit after them. A single leaf is no longer just dead plant material. It becomes the start of a transfer of energy through mud, water, and flesh. That is one of the quiet wonders of mangroves. What falls from the branches does not simply disappear. It is intercepted, transformed, and passed onward, helping support an entire living community from the forest floor outward. Much of a mangrove forest runs on rot, mud, and recycling. It is not a polished ecosystem built on bright petals or dramatic fruit. Much of its power comes from breakdown. Dead leaves accumulate. Wood fragments soften. Organic matter sinks into wet sediment and begins to decompose. What might look messy or lifeless to an untrained eye is actually the engine room of the habitat. Nutrients are being released, transformed, and reused in countless small transactions. Mud holds the products of decay. Microbes work through them. Invertebrates feed, borrow, and stir the mixture into new forms. The whole system is sustained by constant recovery of what has already lived. That gives mangroves a very different mood from forests that seem to celebrate fresh growth alone. Here, death is not the end of usefulness. It is part of the design. Rot is productive. Recycling is relentless. The richness of the place depends not only on what is growing, but on how completely the forest can turn its own leftovers into future life. Their leaf litter feeds microbes before it feeds crabs, fish, and birds. The first diners are often invisible. Before larger animals benefit from fallen plant material, microbes begin softening, digesting, and altering it at a scale too small for us to watch directly. Bacteria and fungi colonize the litter, changing its chemistry and making its nutrients more accessible to the rest of the ecosystem. That sequence matters because it means the forest is processed from the bottom up. The grander animals we notice depend on an earlier feast happening in silence. By the time a crab tears at softened debris, or a food chain carries that energy upward toward fish and birds, the microbes have already done crucial work. I find that deeply satisfying because it reshapes our sense of importance. The health of a spectacular tidal forest is tied to the labor of organisms small enough to vanish from casual attention. In mangroves, the unseen comes first, and the visible richness of the habitat rises from that hidden beginning. Mangrove mud can smell of sulfur because life is thriving without oxygen. That sharp, egg-like scent can catch people by surprise, and once noticed, it is hard to forget. It comes from chemical processes that flourish in oxygen-poor sediment, where certain microbes continue breaking down organic matter by using other compounds instead. In the course of that hidden metabolism, sulfur-containing substances can be transformed into gases with a distinctive smell. What seems unpleasant at first becomes fascinating once you understand what it means. The odor is evidence of intense biological activity in a place where ordinary aerobic life would struggle. Beneath the surface, the mud is busy with organisms exploiting conditions that exclude many others. The forest floor is not inert. It is chemically alive in unusual ways. I love how mangroves can teach this lesson through the nose as much as the eye. Even the smell of the mud tells you that the ecosystem is operating by rules that differ from the ones most people know on dry land. Hidden bacteria in mangrove sediments drive chemistry that shapes the whole habitat. Beneath your feet, the mud is crowded with microscopic chemists. These bacteria help control how nutrients move, how organic matter breaks down, and how elements such as nitrogen and sulfur change form within the sediment. Because of them, the forest floor is not just a storage place for debris. It is an active laboratory. Their work influences water quality, root conditions, and the availability of materials that other organisms need. It even affects which chemical stresses are eased and which are intensified below the surface. That is astonishing when you pause to think about it. An entire visible habitat of trees, crabs, fish, and birds is partly shaped by invisible communities in the mud. The roots above are important, but so is the bacterial world beneath them. Mangroves become even more compelling when you realize they operate on many scales at once. The grandeur of the forest depends in part on microscopic reactions happening in darkness below every step. Mangroves store extraordinary amounts of carbon in their soaked soils. When people think of carbon storage, they often imagine thick trunks, vast forests, and wood standing high above the ground. Mangroves tell a more surprising story. Much of their remarkable storage happens in the waterlogged soils below them, where organic matter can accumulate and remain for long periods under conditions that slow complete decay. That makes these coastal forests important far beyond their shorelines. They are not only nurseries, barriers, and habitats. They are also long-term reservoirs in the planetary carbon cycle. What fascinates me is the contrast between appearance and function. A muddy tidal forest may seem small or ragged compared with towering inland woodlands. Yet the ground beneath it can hold immense stores of carbon-rich material. The most important part of the vault is often out of sight. In mangroves, value is hidden under the mud, saturated, dark, and quietly doing work that matters on a global scale. Much of their carbon is buried below ground, not just locked in wood. That detail changes the whole picture. If carbon was stored mainly in trunks and branches, you could understand the forest simply by looking at it. With mangroves, much of the story lies under the surface, where roots, dead plant material, and accumulated organic matter become incorporated into saturated sediments. The soil itself becomes the archive. Year after year, more carbon-rich material is added, and because the conditions are wet and often low in oxygen, decomposition can be slowed enough for those deposits to build. This means the forest's hidden half can matter as much as the visible one. A stand of mangroves is not only a collection of living trees. It is also a deep storehouse beneath them, layered with the remains of past growth. I think that is one of the most mind-changing facts about these ecosystems. Their greatest significance is not always in what rises above the tide, but in what quietly accumulates below it. Mangrove carbon can remain buried for centuries if the soil stays undisturbed. Time behaves differently in saturated ground. When sediments remain wet and relatively stable, organic material can avoid rapid breakdown and persist for very long periods. In mangrove settings, that means carbon from old roots, leaves, and other plant remains may stay buried for centuries, locked into layers that build slowly beneath the forest. There is something profound about that patience. A tidal landscape that seems restless on the surface can become a keeper of very old material underneath. Each layer is a kind of memory, preserving traces of what once grew there. That makes the soil feel almost historical. It is not just dirt beneath modern trees. It is a record of long accumulation. The forest above may sway with every tide, yet the buried carbon below can endure through generations of storms and seasons. Mangroves teach a beautiful contradiction. A place of constant motion can also become a place of astonishing long-term storage. Destroying mangroves can release old carbon back into the atmosphere. This is where the hidden storehouse becomes fragile. When mangrove soils are dug up, drained, or otherwise disturbed, the conditions that protected buried carbon can change dramatically. Material that remained locked away in wet sediment may become exposed to oxygen and begin breaking down more rapidly, sending carbon back into the atmosphere. That makes the loss of a mangrove forest more serious than the removal of trees alone. It can turn a long-kept reserve into a new source of emissions. I think this is one of the clearest examples of why mangroves matter far beyond their own shorelines. Damage does not stay local. What happens in the mud can echo into the broader climate system. That is a sobering thought, but also an illuminating one. It reveals how much value is concealed beneath the visible forest. When mangroves are destroyed, we do not only lose habitat and protection, we can also awaken carbon that had been sleeping for ages. A mangrove forest can store more carbon than many inland tropical forests. That comparison surprises a lot of people, and it should. Mangroves do not usually look bigger, taller, or more majestic than famous inland forests. They can appear scrappy by comparison, broken into tidal edges and muddy channels. Yet when their full carbon storage is counted, especially the deep reserves in the soil, they can rival and even exceed many tropical forests farther inland. It is a wonderful reminder that ecological importance is not always obvious to the eye. Grandeur and function do not always wear the same costume. A coastline of twisted roots may hold more climate significance than a casual observer would ever guess. I love that reversal because it makes mangroves feel like one of nature's great hidden champions. They do not announce their power with height alone. They keep much of it underground, in saturated layers no tourist photo can capture. Their real scale emerges only when you understand what lies beneath the mud. Their muddy soils are among the planet's richest natural carbon vaults. A vault does not have to be made of steel. In mangroves, it is made of mud, water, roots, and time. Year after year, organic material settles into the saturated ground and becomes buried in conditions that slow its return to the air. The result is a storehouse that can grow quietly beneath a forest many people might overlook from a distance. That is what makes this fact so astonishing. One of Earth's richest natural carbon reserves is not hidden in a mountain, a mine, or a machine. It lies under coastal trees standing in wet sediment at the edge of the sea. The ground itself becomes a keeper of ancient biological remains, holding them in dark layers below the tide. Once you understand that, mangrove mud no longer seems ordinary or messy. It feels precious. A place that stains your boots and smells of salt can also be one of the planet's most important long-term safes. Mangroves blunt storm surges by adding friction to fast-moving water. Storm surge is frightening because it moves with force, pushing seawater inland in a broad, destructive rush. Mangroves can interfere with that movement in a wonderfully physical way. Their trunks, roots, and low vegetation create resistance, forcing water to slow, split, and lose some of its momentum as it passes through the forest. In other words, the surge has to work harder to move forward. That matters because even a partial reduction in speed and energy can make the difference between severe damage and something less catastrophic. I find this deeply impressive because it is such an elegant defense. The forest does not have to block the sea completely to matter. It simply has to make the water fight its way through a living obstacle course. Every root and stem contributes. What looks tangled and irregular becomes useful in a crisis. Mangroves turn rough natural structure into protection by transforming movement itself. They can reduce erosion by holding coastlines together with dense root webs. A bare coast is vulnerable. Waves tug at loose sediment. Currents carry grains away. Banks slump and edges retreat. Mangroves respond to that instability with roots that spread, branch, and interlock through the soil like a living net. Those root webs help bind sediment in place and make it harder for water to strip the shoreline apart. It is one of the most satisfying examples of nature solving a structural problem without concrete or steel. The forest does not simply sit on the coast. It grips it. That grip matters over years, because erosion is often less about one dramatic moment and more about repeated wearing away. Mangroves resist that slow theft of land. They help shorelines keep their shape. There is something beautiful in that image. A forest that appears messy above ground is below the surface, acting with remarkable cohesion, stitching the coastal margin together thread by thread through its roots. After cyclones, villages behind mangroves often suffer less damage. This is where the story becomes human in a very immediate way. A mangrove forest is not only an ecological wonder or a scientific curiosity. In places exposed to tropical storms, it can stand between a village and a more violent encounter with wind-driven water. Where these forests remain intact, people behind them may experience less erosion, less wave energy, and less destruction to homes, fields, and infrastructure than places left fully exposed. That does not mean mangroves erase danger. Cyclones are powerful and unpredictable, but the presence of a forest can still soften the blow in meaningful ways. I think that is one of the most compelling reasons to care about them. The benefit is not abstract. It reaches families, fishing communities, and coastal settlements whose lives are tied closely to the shore. A tangle of roots and trees can become part of a community's protection long before the storm clouds even begin to form. Mangroves can protect coral reefs by trapping sediment before it smothers them. Coral reefs need light and relatively clear water to thrive. Too much suspended sediment can cloud the sea, settle over coral surfaces, and interfere with the delicate life built there. Mangroves help upstream in that story by catching and holding sediments that arrive from rivers, runoff, and disturbed land before all of it reaches the reef. Their roots slow the water, giving particles a chance to settle in the mangrove zone instead of drifting farther offshore. I love this connection because it links two habitats that many people imagine separately. The muddy forest and the bright reef may look like opposites, yet one can help defend the other. The mangrove acts almost like a buffer, intercepting some of the material that would otherwise become a problem in clearer waters beyond. That makes the coastal system feel beautifully cooperative. Protection does not happen in one place alone. Sometimes the reef's survival begins in the mud. They also help seagrass beds by calming water and filtering runoff. Seagrass meadows may look delicate, but they depend on the right physical conditions to flourish. Water that is too murky, too turbulent, or too loaded with land-based runoff can make life harder for them. Mangroves can improve that situation from the shoreward side. By slowing currents and capturing some of the material washing off the land, they help create calmer, cleaner coastal waters where seagrasses have a better chance to grow. That relationship is wonderful because it shows how one habitat prepares the conditions for another. The mangrove does not have to touch every blade of seagrass to matter. It helps shape the surrounding environment in ways that make underwater meadows more viable. This is one of the great pleasures of learning about coasts. Nothing stands entirely alone. A forest rooted in mud can influence a field of plants growing under shallow water some distance away, simply by moderating what arrives there. Mangroves, seagrasses, and reefs often function like one connected coastal system. It is tempting to divide the coast into separate scenes. Here is the mangrove. There is the seagrass bed. Farther out lies the reef. In reality, these places often operate more like linked neighborhoods in one larger living network. Water moves between them. Nutrients move between them. Animals may spend different stages of life in each one. What happens in the nearshore forest can influence conditions in the meadow, and what happens in the meadow can affect the reef beyond. This makes the coastline feel less like a row of habitats and more like a conversation unfolding across distance. I find that idea deeply satisfying because it replaces isolation with relationship. The health of one part often depends on the others holding together. A break in the chain can ripple outward. When mangroves, seagrasses, and reefs all remain intact, the coast works with greater balance, richness, and resilience than any single piece could achieve on its own. The health of offshore fisheries can depend on forests rooted in mud. That is a marvelous twist, because the connection is easy to miss if you only look at the open water where fish are caught. Offshore fisheries may seem like the product of distant seas alone, yet some of the species people depend on begin life or find early shelter near mangrove coasts. Others benefit indirectly from the food webs and water quality those forests support. This means a muddy shoreline can influence the abundance of fish much farther from land than most people would guess. The implication is profound. Remove the forest, and you may weaken the fishery. Protect the forest, and you help sustain life that later moves outward into bays, channels, and offshore grounds. I think that changes the way one sees a mangrove edge. It is no longer just a local habitat. It becomes part of the foundation for livelihoods, meals, and economies tied to the sea. A commercial catch may begin with roots in mud. Mangroves can improve water quality by trapping pollutants and excess nutrients. Water arriving from the land often carries more than fresh runoff. It may also bring sediment, fertilizers, and other pollutants that would be harmful if they rushed straight into coastal waters unchecked. Mangroves can slow that flow and help retain some of the unwanted load within their complex root zones and sediments. In effect, the forest buys time and space for the system to process what arrives. That does not make mangroves indestructible, and it does not mean they can absorb limitless pollution. But it does mean they play an important cleaning role at the boundary between land and sea. I think this is one of the most quietly impressive services they provide. They are not only dramatic habitats full of strange roots and wildlife, they are also working landscapes that can help moderate the consequences of what humans wash downhill. A mangrove forest can improve the quality of water simply by standing where trouble arrives first. They are natural filters, standing exactly where land runoff meets the sea. That location is everything. Mangroves occupy the meeting point where rivers, drains, and surface runoff deliver the products of the land toward coastal waters. Because they stand in that path, they are perfectly placed to intercept sediment, nutrients, and other materials before those substances spread farther outward. The roots slow water. Particles settle. Biological processes in the mud and among the plants begin handling what has arrived. It is a beautifully strategic position, almost as if the forest had been stationed there on purpose. Of course, evolution placed it there for its own reasons, but the result feels uncannily useful. Mangroves become living checkpoints between two worlds. They do not merely survive at the coast, they process it. Everything moving seaward has to negotiate with them first. That gives these forests a special kind of importance. They are not just coastal scenery. They are active boundary keepers at one of the most consequential edges on Earth. Some mangrove coastlines are slowly moving poleward as winters grow milder. Mangroves are creatures of warmth, and for a long time, cold winters helped draw a firm line around where they could survive. In some regions, that line is now shifting. As severe freezes become less frequent, these forests have begun appearing farther from the equator than they once could. It is a subtle migration, not a dramatic march, yet it changes the map all the same. A shoreline that once belonged mainly to salt marsh plants may begin to host young mangroves instead. Over time, the character of the coast can start to transform. New roots appear. New shade develops. New habitat forms for the animals that can use it. I find that fascinating because it shows a forest responding to climate not by standing still, but by redrawing its frontier. The edge of the mangrove world is not fixed forever. In some places, it is quietly advancing into territories that were once too cold to hold it. Cold snaps can suddenly kill mangroves at the edge of their range. For all their toughness against salt, mud, and tides, mangroves still carry a weakness that can undo them with brutal speed. A sharp freeze can damage tissues, kill leaves, and, in severe cases, wipe out whole stands near the cooler limits of their distribution. That contrast is striking. A tree that survives seawater and shifting ground can still be brought down by a hard burst of cold air. Along range edges, this makes the forest feel precarious in a way people do not always expect. One stretch of mild years may allow expansion. Then a sudden cold event can reverse the story almost overnight. Branches blacken. Growth stops. Shorelines that looked newly claimed may become bare again. It is a reminder that ecological boundaries are often enforced by rare extremes more than average conditions. Mangroves can flirt with cooler coasts, but winter still holds veto power where the climate remains uncertain. Sea level rise can help or harm mangroves, depending on space inland. At first, the idea sounds contradictory. More water might seem like a simple threat to a coastal forest, yet the reality is more complex. Mangroves are already adapted to tidal flooding, so rising seas do not automatically destroy them. In some places, if the slope is gentle and undeveloped land lies inland, the forest can gradually shift landward and keep its place within the tidal zone. In other places, that path is closed, and the same rising water becomes a trap. This dual possibility is what makes the subject so compelling. Sea level rise is not one single outcome for mangroves. It is a test of whether the coast can move with the water. A flexible shoreline may allow adjustment. A constrained shoreline may bring loss. That means the future of these forests depends not only on the ocean itself, but on what lies just behind them, waiting either to receive the forest or prevent its retreat. If seawalls block retreat, rising seas can squeeze mangroves out entirely. This is one of the harshest coastal ironies. A seawall may be built to defend land, but when it stands directly behind a mangrove forest, it can leave the trees with nowhere to go as sea level rises. Water advances from the front. Hard infrastructure blocks movement from the back. The forest is pinched between them until the tidal zone narrows beyond what the mangroves can tolerate. This process is often called coastal squeeze, and the name fits perfectly. There is a sense of pressure, of a habitat slowly losing room to breathe. What makes it so striking is that the problem is spatial before it is biological. The trees may still be capable of living in tidal conditions, yet the geography no longer permits the necessary shift inland. The future disappears because the path disappears. A living coastline can be erased not only by water itself, but by the walls that refuse to let the coast move. Mangroves can keep pace with rising water only if mud keeps arriving. A mangrove forest does not survive rising seas by wish alone. It needs the ground beneath it to rise as well, or at least not fall behind too badly. That is where incoming sediment becomes crucial. Mud delivered by rivers, tides, and coastal currents can accumulate within the root zone, helping build the soil surface upward over time. Organic matter from the plants themselves can also contribute. Together, these processes may allow the forest floor to maintain its position within the tidal frame. But if sediment supply drops too low, the balance becomes dangerous. Water keeps rising while the ground fails to keep up. I find this mesmerizing because it turns mud into destiny. Something as humble as fine sediment can decide whether a forest holds its place or drowns. Mangroves are not only battling the sea with roots and salt tolerance. They are depending on a steady gift of earth to remain in the game. Too much pollution can suffocate mangrove roots beneath oily or dirty films. Mangrove roots rely on contact with air and water in very particular ways, which means pollution can strike at the forest's most vulnerable interface with its environment. When oily residues or heavy surface contamination coat sediments and roots, gas exchange can be disrupted, and the normal functioning of exposed tissues can be impaired. The result is a kind of choking. The forest is still standing, but the pathways it uses to breathe and manage stress are being blocked. That is one reason pollution can be so devastating in mangrove habitats. The damage is not always loud or dramatic at first. It can spread as a smothering film, creeping over the very structures the trees need most. I think that makes the threat especially haunting. A mangrove survives tides, salt, and unstable ground through exquisite adaptation, yet a layer of human waste can silence those adaptations by sealing the forest under a dirty skin it never evolved to escape. Shrimp farming has destroyed vast areas of mangroves in some countries. The change can happen with brutal simplicity. A tidal forest is cleared, the roots are removed, and the land is converted into ponds for shrimp production. From above, what was once a maze of living channels becomes a geometric grid. This is one of the most dramatic ways mangrove landscapes have been transformed in parts of the world. The loss matters not only because trees disappear, but because an entire coastal system is stripped away with them. Nursery habitat vanishes. Shoreline stability weakens. The buried richness of the soil is disturbed. What makes this especially striking is the trade being made. A complex, self-sustaining ecosystem that evolved over long periods can be replaced very quickly by a much simpler and more fragile human use. Even when the farms later fail or are abandoned, the original forest does not simply snap back into place. The cost of that conversion can echo long after the ponds stop producing. Clearing mangroves often harms fisheries that people depend on for food. The connection is easy to ignore until catches begin to fall. Remove the forest, and you do not only lose trees. You also remove sheltered habitat, food pathways, and coastal structure that many fish and shellfish species rely on during key parts of their lives. That can ripple outward into nearby waters and ultimately into human kitchens and markets. For communities that depend on fishing, the consequence is not theoretical. It may mean smaller catches, less reliable income, and greater pressure on already strained marine resources. I think this is one of the clearest examples of how ecological damage becomes social damage. Mangroves may look like remote thickets to someone passing by, yet they are tied directly to food security in many coastal regions. A chainsaw on the shore can eventually be felt in an empty net offshore. The forest feeds people even when no one is harvesting anything from the trees themselves. Restoring mangroves is harder than simply planting rows of seedlings. Planting trees feels like an obvious solution, and in some settings it can help, but mangroves are not ordinary forests growing on ordinary ground. Their success depends on tidal flow, sediment conditions, salinity patterns, elevation, and the subtle shape of the shoreline. If those ingredients are wrong, neat rows of planted seedlings may struggle, fail, or create a false impression of recovery without restoring the full ecosystem. That is why mangrove restoration can be far more demanding than it first appears. You are not just replacing trunks. You are trying to rebuild a relationship between land and water. I find that both humbling and fascinating. It reminds us that a living coast cannot always be repaired by the same logic used for a park or plantation. The deeper challenge is to restore the processes that allow the forest to sustain itself. When those return, the trees have a real chance. Without them, planting alone is often wishful thinking. A mangrove forest needs the right tides, mud, slope, and water flow. This is the hidden recipe behind the whole habitat. You can have warm weather and suitable species nearby, yet still fail to grow a healthy mangrove forest if the physical setting is wrong. The tide must reach with the proper rhythm. The mud must have the right texture and chemistry. The ground must sit at an elevation the water can flood but not overwhelm. The slope must allow that interaction to happen naturally. Water has to move enough to connect the system, but not in a way that scours everything away. When all of that aligns, mangroves can flourish with astonishing vitality. When it does not, even well-meant restoration can falter. I love this fact because it reveals how deeply these forests are shaped by choreography rather than chance. Mangroves are not simply trees placed near the sea. They are the living expression of a very specific coastal balance between motion, sediment, height, and time. Some failed restoration projects planted the wrong species in the wrong zone. It sounds like a small mistake, but in a mangrove landscape it can undo an entire restoration effort. Different species belong in different parts of the tidal gradient. One may prefer the seaward edge. Another may thrive farther inland where flooding is less intense. Put them in the wrong place, and the seedlings may struggle from the start, not because the idea of restoration is flawed, but because the forest has its own rules. That is what makes some failed projects so fascinating and so instructive. People can arrive with good intentions, neat rows, and thousands of young plants, then discover that a mangrove coast is not a blank canvas. It is a living pattern shaped by salt, elevation, and the pulse of water. Restoration succeeds best when it listens before it acts. The forest already knows where each kind of tree belongs. The challenge is learning to read that arrangement correctly. When hydrology is repaired, mangroves can sometimes return on their own. This is one of the most hopeful truths in the whole mangrove story. In some damaged places, the trees do not need to be planted one by one if the water is allowed to move properly again. Open the blocked channel. Remove the barrier. Restore the natural tidal rhythm. Once the flooding pattern, salinity, and drainage begin to resemble the old system, mangroves may reappear with surprising grace. Propagules arrive on the water. Seedlings settle where conditions finally suit them. The forest begins writing itself back into the landscape. I think that is extraordinary because it shows that recovery is not always about forcing life into place. Sometimes it is about giving a damaged coast back the physical conversation it once had with the sea. When that dialogue resumes, the habitat can begin healing from within. The returning trees feel less like replacements and more like a memory the shoreline has been waiting to express again. Local communities have protected mangroves for timber, fish, and storm safety. Mangroves are often defended not only by laws or scientists, but by the people who know them as part of daily life. In many coastal places, local communities have long understood that these forests provide practical value worth guarding. They offer useful wood. They support fish and shellfish that feed families and sustain livelihoods. They also stand between settlements and damaging weather. That combination creates a powerful reason to protect them. It is not sentimental. It is grounded in lived experience. People notice when catches improve near healthy forests. They notice when shorelines hold together better. They notice what disappears when mangroves are cut. I find that deeply compelling because it reminds us that conservation is often strongest when it grows from close familiarity. The people who live beside these forests may know their importance not from abstract theory, but from tides, storms, nets, boats, and years of watching what the coast does when the trees remain. Mangrove wood resists rot so well it has long been highly valued. That quality makes perfect sense once you remember where mangroves live. These trees spend their lives in wet, salty, demanding conditions, so the wood they produce is often dense, durable, and notably resistant to decay. For people living near the coast, That durability has made mangrove timber especially useful for posts, poles, fuel, and other practical needs. There is something satisfying about that continuity between habitat and material. A tree forged in harsh conditions yields wood suited to hard service. It carries the resilience of the environment into the objects people build from it. Of course, that value has also created pressure, because a highly useful forest can be overcut when demand outpaces care. Still, the wood itself remains fascinating. It is another example of mangroves turning adversity into strength. Even after the tree is cut, the qualities it developed in mud, tide, and salt continue to show in the toughness of the timber. In some places, mangroves supplied charcoal, dyes, medicines, and building poles. Few forests offer such a practical range of gifts from one landscape. In different coastal cultures, mangroves have provided fuel in the form of charcoal, coloring agents derived from bark rich in tannins, medicinal uses rooted in local knowledge, and sturdy poles for building kra. This variety is one reason the relationship between people and mangroves runs so deep. The forest was not just scenery at the edge of the village. It was part of working life, trade, craft, and survival. I love that because it makes the habitat feel culturally alive as well as biologically rich. A mangrove could warm a cooking fire, tint a material, support a structure, or contribute to traditional healing practices. Each use depended on close observation of what different species could offer. The result is a history of intimacy with the coast, where people learned the properties of these tidal trees and folded them into everyday life. Traditional fish traps were sometimes built directly within mangrove channels. That placement was no accident. Mangrove channels are natural routes of movement, with fish passing in and out on the tide through narrow waterways that can be read and used by people who know them well. In some places, traditional traps took advantage of that rhythm by being set where the current, the channel shape, and the daily pulse of the water would guide fish toward them. It is a beautiful example of human skill meeting ecological understanding. The trap did not overpower the landscape. It worked with it. Knowledge of tides, fish behavior, and the layout of the routes all came together in a design shaped by patience and observation. What fascinates me most is the intelligence of the placement. A mangrove creek might look tangled or confusing to an outsider, yet to experienced coastal communities, it could be read almost like a text, each bend and flow suggesting where opportunity would pass. Honey gatherers enter mangroves seeking hives hidden high above the tide. There is adventure in that image before you even know the details. The gatherers move into a landscape of mud, channels, roots, and insects, looking upward as much as downward. Somewhere above the reach of the water, bees have built hives in branches that sway over a tidal world. Reaching them can require courage, balance, timing, and deep knowledge of the forest. I think this is such a captivating detail because it joins sweetness to difficulty in a very direct way. Honey, which feels domestic and comforting in a jar, begins here in a far more dramatic setting. It must be sought in a forest that can flood, sting, confuse, and surprise. That contrast gives the practice a storybook quality, yet it is entirely real. The mangrove becomes not only a place of roots and fish, but a place where people climb toward hidden stores of nectar made high above the shifting tide. Some coastal cultures read tides and roots like a living map. To an outsider, a mangrove forest can look bewildering. The channels twist. The water level changes. The roots repeat themselves in patterns that seem impossible to memorize. Yet for people who know these coasts intimately, the forest can be read with remarkable confidence. The rise and fall of water tells time. The shape of roots and banks hints at depth, current, and safe passage. Subtle signs reveal where a channel leads, where fish may gather, or where travel will be easiest on a given tide. That kind of knowledge is extraordinary because it turns a place many find confusing into one rich with direction and meaning. The map is not drawn on paper. It is embodied in memory, experience, and attention. I love that because it shows how deeply humans can learn a landscape when survival and tradition depend on it. The forest becomes legible, but only to those who have truly studied its living language. Mangroves can preserve ancient shorelines and clues to past sea levels. A modern mangrove forest can hold evidence of coastlines that existed long before any person standing there was born. As sediments accumulate and organic material is buried, traces of former shore positions can be preserved in layers beneath the present habitat. Scientists can study those layers to infer where the coast once lay and how sea level changed through time. That makes a mangrove not only a living ecosystem, but also a kind of coastal archive. Beneath the roots and mud, history waits in physical form. I find that profoundly exciting because it means these forests connect present life with vanished landscapes. The shoreline we see today is only the latest version. Earlier edges of land and water still linger below, recorded in buried sediments and ancient organic remains. Mangroves help keep those records because they trap material and build ground over it. The forest becomes a place where the past is not gone. It is layered underfoot. Their peat-like soils hold records of storms, sediment, and changing climate. Think of the ground as pages rather than mud. Over long spans of time, mangrove soils can build in layers, each one preserving something about the conditions under which it formed. A storm may leave a distinct deposit. A shift in sediment supply may alter texture or composition. Changes in climate can influence vegetation, salinity, and the organic matter entering the soil. When researchers examine those buried sequences, they can sometimes reconstruct pieces of the environmental story that produced them. That is astonishing to me because the forest floor becomes more than support for roots. It becomes an archive with a memory of tempests, quiet periods, and broader change. The record is not written in words, yet it can still be read with care. In that sense, mangroves are historians as well as habitats. Their dark, saturated soils quietly preserve traces of events that passed long ago, waiting for someone to learn how to listen. Scientists study mangroves to understand resilience in extreme and unstable environments. A mangrove forest is a kind of natural stress test. The trees endure flooding, salt, heat, unstable sediment, and constant physical disturbance. Yet many still manage to grow, reproduce, and support astonishingly rich ecosystems. That is why scientists find them so valuable. These forests reveal how life persists when conditions are difficult, changeable, and often close to hostile. Researchers can ask how roots function in oxygen-poor mud, how tissues manage salt, and how whole communities recover after storms or environmental shocks. Each answer helps build a broader understanding of resilience, not only in mangroves themselves, but in living systems more generally. I think that is one of the most exciting things about them. They are not just interesting because they are unusual. They are useful because they teach. A mangrove coast becomes a living classroom where survival is not abstract. It is visible in every root, leaf, channel, and returning tide. Engineers copy mangrove roots when designing better barriers and coastal defenses. When engineers look for ideas, they do not always begin with concrete. Sometimes they begin with a forest. Mangrove roots have evolved to interact with moving water in ways that reduce force, slow flow, and remain stable in soft ground. That makes them deeply interesting to people designing coastal protections. Instead of asking only how to block waves with a hard wall, engineers can ask how a branching structure might absorb energy, redirect water, and remain effective without needing to behave like a solid barrier. The inspiration comes from the shape, spacing, and flexibility of the roots themselves. Nature has already been running experiments in coastal design for ages, and mangroves are among its most impressive results. I love that crossover between biology and engineering. A tree that survives in mud can influence how humans think about defense, materials, and flow. The forest becomes not only something to protect, but something to learn from and emulate. Their root patterns inspire ideas for architecture, robotics, and water flow design. Mangrove roots are not random tangles. They are forms that solve multiple problems at once, and that makes them incredibly appealing to designers. They distribute weight, create stability, manage flow, and fill space with branching patterns that are both efficient and adaptable. Architects study such forms when thinking about support systems in difficult terrain. Roboticists find inspiration in structures that can navigate or anchor in unstable environments. Designers interested in water movement examine how root networks alter current and turbulence without functioning like a blank wall. What fascinates me most is the generosity of the pattern. One biological structure offers lessons across completely different fields because it balances strength, flexibility, and complexity so elegantly. Mangroves remind us that useful design does not always look neat or symmetrical from a distance. Sometimes the smartest structure is branching, irregular, and alive with variation. The forest becomes a library of shapes waiting for human imagination to translate. Mangroves show how a tree can survive drowning, salt, heat, and shifting ground. If someone described those conditions before you saw the forest, you might assume no tree could possibly manage them all together. Too much water would drown the roots. Too much salt would pull moisture from tissues. Too much heat would intensify stress. Unstable ground would undermine support. Yet mangroves meet all of those pressures at once and keep living. That is why they feel so extraordinary. They force us to broaden our idea of what a tree can be. Instead of imagining a plant rooted in stable soil beneath fresh rain, we find a different model entirely, one built for compromise, adjustment, and constant negotiation with a difficult world. Each adaptation is impressive on its own, but taken together they become something close to astonishing. The mangrove is not merely tough in one direction. It is resilient across several forms of hardship at once. That combination is what gives the forest its almost unbelievable character. Few forests on Earth are forced to negotiate with the sea every day. Most forests do not have to bargain with incoming tides. They are not asked twice daily whether they can tolerate floodwater, shifting salinity, moving sediment, and the rearranging force of a living coastline. Mangroves are. Their existence depends on a continual exchange with the sea, and that makes them different in spirit as well as form. They are not simply rooted beside the ocean. They are in active relationship with it, responding to its rhythms day after day. I find that idea deeply compelling because it makes the forest feel almost diplomatic. Nothing is entirely settled. The sea advances, the forest endures, and both shape the edge they share. That repeated negotiation gives mangroves a special tension and beauty. They are never completely land and never completely marine. They belong to an argument between the two, one that has gone on for ages and is still being worked out with every returning tide. Mangroves are trees, but they behave like expert survivors of another world. That is part of their enchantment. They possess trunks, leaves, bark, and roots like other trees, yet so much about their lives feels unfamiliar once you look closely. They grow in salt. They breathe through exposed structures. They reproduce with drifting young. They stand in places that flood, soften, and shift beneath them. All of that gives them a strangely alien quality, as if they were trees rewritten for a planet with different rules. and yet they are fully of this earth, which somehow makes them even more impressive. Nature did not need to invent a fantasy organism to occupy that harsh coastline. It transformed a tree into something capable of thriving there. I think people respond strongly to mangroves because they challenge what a tree is supposed to look like and where a forest is supposed to belong. They seem both familiar and impossible at once, which is one of the most captivating combinations in nature. At high tide, a mangrove forest becomes half land and half sea. The transformation can feel almost theatrical. Water rises through channels, around trunks, and into spaces that only hours earlier were exposed mud. The lower world of roots is submerged. Fish and other aquatic life move into places that were dry enough to walk across before. The forest still stands, but its meaning changes with the tide. It is no longer simply a woodland at the edge of water. It becomes a flooded architecture, a place where branches belong to air and lower roots belong to the sea at the same time. I love that duality because it turns the landscape into something wonderfully unstable in identity. You cannot describe it fully with one category. It is both grounded and aquatic at once. That makes high tide in mangroves feel like a reveal, as though another version of the forest has quietly arrived and taken possession of the same space without moving a single tree. At low tide, the same forest reveals crabs, roots, and breathing mud. Then the water drains away, and the hidden world returns to view. What had been submerged becomes exposed, textured, and busy with details that high tide concealed. Roots emerge in their full strangeness, arching, stabbing upward, or spreading across the surface in patterns that can seem almost sculptural. Crabs appear in motion, crossing the mud or vanishing into burrows. The ground itself seems to breathe through openings, wet sheen, and the exposed structures of the trees. It is one of the most satisfying reversals in nature. The same place becomes legible in an entirely different way just because the tide has withdrawn. I think that is why mangroves hold attention so powerfully. Their reward return visits within a single day. One tide gives you the aquatic version of the forest. The next gives you the muddy mechanical version, full of surfaces, labor, and forms that were hidden only a short time before. Mangroves turn an inhospitable coastline into one of Earth's richest habitats. This may be the most astonishing thing about them all. Start with a difficult place: salty water, unstable mud, low oxygen, intense sun, and a shoreline reshaped by tides, and you would not expect abundance. You might expect emptiness or only a few hardened survivors. Mangroves overturn that expectation completely. Once established, they create shelter, structure, food pathways, and opportunities for life at many levels. The result is a habitat that supports an extraordinary concentration of organisms, from microbes in the sediment to birds in the canopy and predators in the channels. That transformation is what makes them feel almost miraculous. They do not merely tolerate a hostile setting, they convert it into possibility. I think that is why people who learn about mangroves often become captivated by them. They are proof that richness can emerge from conditions that seem, at first glance, entirely unpromising. The forest makes the impossible coast livable. Once you understand mangroves, no muddy shoreline ever looks ordinary again. That may be the most lasting gift of learning about them. Beforehand, a muddy tidal coast can seem messy, flat, and easy to dismiss. Afterward, the same place feels layered with ingenuity, hidden labor, and living drama. You begin to see roots as engineering. Mud becomes habitat and archive. Tides become transport, timing, and transformation. Birds, fish, crabs, microbes, and trees all start to appear as part of one intricate conversation between land and sea. The shoreline has not changed, yet your vision has. That is what makes mangroves such a satisfying subject. They train the eye and the imagination at the same time. Once you know what is happening there, even an apparently quiet patch of coast begins to feel crowded with stories. I love that shift because it is more than information. It is a new way of seeing. The ordinary dissolves, and the edge of the sea becomes wonderfully permanent to strange. As we come to the end of our journey, the shoreline begins to soften in the mind. We have wandered through forests that stand where land and sea meet, where roots rise into the air and sink into shifting mud, where tides arrive and retreat like a steady breath. We have seen how life gathers here in remarkable ways, from tiny unseen workers in the soil to birds above the canopy, from drifting seedlings to powerful predators moving through quiet channels. What first seemed like a tangled, uncertain place reveals itself as something deeply ordered, deeply connected, and quietly extraordinary. And now you can let those images drift a little further. Picture the water rising and falling, slow and steady. Picture the roots holding their place as the tide moves around them. Nothing rushes here. Nothing needs to be forced. The forest simply exists, adapting, enduring, and continuing on. If you are still awake, you might like to follow this calm into another story. There will be another video waiting for you on the screen, ready to carry you somewhere new. And if not, just rest here for a moment longer. Let your breathing settle into a gentle rhythm. Let your thoughts move like the tide, coming and going without effort. There is nowhere else you need to be. Sleep well, and good night.